Hi everybody, in this video on Calculus 2 by example, we're going to look at two examples of determining the convergence or divergence of an infinite series. Okay, and in this video we're going to focus on how convergence and divergence is defined for infinite series. So this is an infinite series or a series, and it's a summation, an infinite summation from I equals 0 to infinity of 1 minus 1/2 to the I. So the first term would be 1 minus 1, and then it'd be 1 minus 1/2, then 1 minus 1/4, then 1 minus 1/8, and we're adding those up. To determine the convergence or divergence of an infinite series in Calculus 2, we look at the sequence of partial sums. So this is a typical partial sum. So instead of going from 0 to infinity, we're just adding up the first n plus 1 terms, where we add from I equals 0 to I equals n. Okay, so we're just adding up a small piece of our series and then asking what happens to those pieces as n gets larger and larger. Okay, so first of all, if I'm adding up n plus 1 copies of 1, that gives me a copy of n plus 1. And then I need to subtract off what happens when I add up these copies of 1/2 to a power. But over here on this right-hand piece, this right-hand term, that is an example of a geometric summation. And geometric summations have a very nice formula for adding them up. So that will be 1/2 to the n plus 1 minus 1. And we're dividing by negative 1/2 because the denominator is 1/2 minus 1. When we simplify this, or rather when we take the limit, this is going to be infinite because the first term goes to infinity and the second term does not. The second term, in fact, will go to 2. Okay? And so this partial sum, as n gets larger and larger, goes to infinity. That means that the series diverges. Another way we can see this, and we'll look at this in more detail later on, is we can compare the series to an integral. So in particular, the series is the summation of all these rectangles, okay? And the height of those rectangles is approaching 1. It becomes almost indistinguishable from 1. So effectively, when we're adding up the terms in the series, it's almost like we're adding up infinitely many rectangles with a height of 1 and a width of 1. And we could compare that to the integral, the improper integral from 1 to infinity of 1 minus 1 over 2 to the x. And if we evaluated that improper integral, that would be infinite as well. Okay, so this is an example of a divergent series, and we focused on seeing that it's divergent by looking at the sequence of partial sums. Let's do the same thing for a convergent series. Here I'm just taking what was sort of the right-hand piece of my previous series, so I'm just adding up the geometric sum piece. Again, we look at a partial sum, so instead of adding from 0 to infinity, we add from 0 to n. But this is a geometric summation, which I said in the previous slide has a very nice formula. Which is 1/2 to the n plus 1 minus 1 over negative 1/2. Then the negative 1/2 is again from 1/2 minus 1. And if we take the limit of that as n goes to infinity, the 1/2 to the n plus 1 goes to 0, so I have negative 1 divided by negative 1/2, which will give me a positive 2. Again, we could compare this to an integral. So S, the terms in S are again the little boxes underneath the curve. And here we can take the integral, the improper integral from 1 to infinity of 1 over 2 to the x dx. And if we were to evaluate that improper integral, we would get a finite value. We'd get a finite area under the curve. And so if there's a finite area under the curve, then this geometric series, this is an example of something called a geometric series, will also be finite. Okay, so that's an example of a divergent series and a convergent series, And we focused on the definition of what it means to be convergent and divergent, which is we looked at partial summations. So rather than looking at the summation from 0 to infinity, we looked at the summation from 0 to n. So those are some examples of determining convergence and divergence using the definition of what it means to be convergent or divergence for a series in Calculus 2. In the next video, we'll focus on convergence tests. Have a good day, and I'll see you then.